Hey, everybody. So as mentioned, my name is Terry Schussler. I work for Deutsche Telekom. I'm the Director of Immersive Technology. My role in the company is to research technology on both the network end and on the device end to figure out how we can bring the two together to create better immersive experiences. So very focused on, in the network side, edge compute and 5G as enabling technologies. And on the device side, I work with a lot of the device manufacturers to understand their roadmaps and inform them on how we can help them achieve their goals. So today what I want to talk about is how we use the technology for edge compute and 5G, or how we will be able to use it to create pervasive AR experiences for end users. Today, we focus mostly on B2B applications with AR and VR, but really focusing on the future of immersive reality, or XR, whatever you want to call it. I'm very interested in the challenges involved in bringing this technology more pervasively to the consumer environment and making it more of a regular, everyday experience. I'm wearing my engineering hat, but I'm going to take it off for a moment. Start focusing on the presentation. So we really today, as you guys know from going down the show floor, don't have this sort of holy grail device. Ideally, I would put my glasses on and they would automatically turn on and I would have an augmented or mixed reality experience. And you wouldn't really know that and you wouldn't care because you also have glasses like that. That's where we're going. And today, the problem that we have with devices is that they're heavy, they're very expensive, and they're very power hungry. So we have these problems with form factor, we have these problems with the comfort, and this is an area that all of the companies in the industry are working very hard to focus on, how to trying to get to that form factor. So most people today walk down the street, they're looking at their phone, and they're not engaging with the real world because they have to hold the phone up, and they get the sort of gorilla arm, sort of experience as they constantly use their phone in their face to try to figure out what they're looking at and get that AR or mixed reality experience. We want to avoid that. We certainly want to avoid situations like this, where you have dedicated walking lanes for people with cell phones separate from people who are actually out in the real world exploring and seeing what's happening around them. So, if you go to a typical dense city location and you just take a moment, take a picture with your phone, of course, of all the people that are in there, you'll see quite a high percentage of people who are, literally walking with their phone as like it's some sort of magic guide to everything that they're doing, and they have no idea that they're about to run into people. So, as we see this transition, focusing on bringing the form factor of devices smaller, bringing the price points down, and of course, very importantly, bringing the weight down, sort of predict this sort of trend of evolution of reduction in the technology required to physically fit into the form factor of the devices. You see transitions with chipsets like the Qualcomm XR1, to provide more onboard technology to enable the devices to perform basic functions that are required for mixed reality experiences. And you also see changes in the way that battery and compute are being distributed on the devices. So, power or energy is a very important factor in making these devices successful. And also, of course, compute challenge is a big one because it deals with energy consumption as well as the physical space required to house that computing. So what we're trying to really focus in on this process is the two pain points of, or opportunities to take the compute and offload it from the device. And some companies are working with this process by taking the compute and offloading it to an EPU or a little battery pack type device that they have attached to their waist. Our goal is to actually take the compute completely offloaded off the body of the person and put it on the network, create network-dependent glass experiences. And so that means that we have to create improved connectivity as well. So let's talk a little bit about edge compute. A lot of people have sort of mixed understandings about what it's all about. It's really, the primary focus is to take the compute functions and put them as close as possible to the user. So, if we look at the distance that data travels today, typically goes hundreds of kilometers, and that takes a certain amount of milliseconds of latency just to get there and get back, and not counting the network transportation manipulation time and also the compute time on the cloud side. So this is a factor that we're trying to address with edge compute. We have two really basic kind of tiers of edge computing. So One is on-site, so on-premise computing, if you will. And so here we would see compute being integrated into smart homes, smart buildings, smart factories, even airplanes. I very much see the future where as you move from your office to the airplane, your virtual desktop experience that you visualize through your glasses is actually running on a VM that's actually on the airplane itself. And then when you land in a new country, that VM instance will instantly jump off the plane onto the nearest edge infrastructure location. So that's what I see is happening in the future. The other form of edge, and this is the area that we're particularly focused on at Deutsche Telekom, is putting edge compute at 5G base stations and also in regional data centers. This is a more efficient and cost-effective way for us to deploy an infrastructure that allows a wide number of people to benefit from the value of edge compute. And we're working very hard. In Germany, for example, we have 4 regional data centers that provide reduction in latency down from the traditional average of about 80 milliseconds that you see today with cloud compute. We're getting around 30 milliseconds now with this edge compute infrastructure that we're building out. So that alone makes a big difference in the experience that users can have. So if you look at the endpoint for the compute, you have your devices, you have connected cars, you have factory environment where you have IoT-based devices, machines robotically controlled, and you need high performance, low latency connectivity in order to enable real-time experiences to operate in this. So with edge compute, we can actually bring the latency down quite significantly. As I mentioned, in these regional DCs, we're able to get it to about 30 milliseconds in our initial test. But our goal is to get it down to around 5 milliseconds. When you get under the 10 millisecond range, some interesting things start to be possible. And you can really achieve some new experiences based on the reduction in the latency that you are able to implement with edge compute. So today we have, of course, the cloud compute being primarily used in a lot of mobile applications rely on cloud compute as a way of offloading certain compute functions. You look at products like Uber as an application, it has something like 1,500 microservices that are all running off of cloud compute infrastructure. And so those services are just-in-time services. They don't have to be real-time in quite the level that we're looking for. With immersive applications, we have a goal of trying to really focus in on enabling things to happen as quickly as possible. And so the benefits of edge compute are to not only reduce the latency, but also improve the quality of service that users get by having a consistent connection, a reliable connection with the network, and also to reduce the dependency on a single point of failure cloud connection that you might have in the backhaul. So by having edge compute infrastructure set up, you can actually have multiple points of connectivity, and even as the user transfers, driving in a car, using their mobile phone, and connecting to edge compute at the nearest 5G base station, that compute challenge can be moved over to a nearer base station as they travel down the road at 60 miles per hour. Also, we can reduce network congestion by keeping the compute and the data transport on premises or as close to the user as possible. So a good example would be if you were to have a webcam running as a security camera feeding a data stream 24 hours a day up to through the public cloud, you'd probably pay Amazon about $3,000 a year in transport costs. But what's possible with edge compute is that we can take that video stream and we can do computer vision processing on it and only send back to the cloud or back to IT management the important information. So when something relevant happens, something different happens, something of concern happens in the video, then we can capture that and transport just that information. And you can see literally a couple of orders of magnitude reduction in transport costs just on that level alone. And as you guys know, the world is very much more of a video upstream world than it was 10 years ago. And so this is a very important part of making the network less congested for everybody. So there's 3 specific use cases that we're focusing on initially with edge compute. So one is the ability to deal with GPS fraud. So right now, it's as simple as downloading an app to go in and fake where your GPS location is. People use this to cheat in games like Pokemon Go and Niantic Ingress. But they also impact businesses like Uber and Lyft. And there's a rampant problem with drivers who are faking the GPS information and changing the fare costs to the rider, and of course, taking money away from the provider. So this is an issue that's problematic, and we can save a lot of cost of these businesses and a lot of customer sort of dissatisfaction by utilizing network-based locationing information operating off of edge compute, because we have the radios, we can triangulate, and we can validate that the GPS location that the user is reporting from their mobile device is in fact correct, and if not, flag it for fraud. So that's a really important and very low-hanging fruit use case for edge compute. Another is that we can take, obviously, the compute offload. You saw in the last presentation some great examples of that. Taking certain tasks off the device that don't have to be on the device. Speech recognition might be a good example as an input modality. You don't necessarily have to have that in real time. As long as the latency is low enough and the processing is quick enough, you can put that on edge, run it off there, and a lot of people do that today with various cloud services. But we can accelerate and make the responsiveness of that better as we deal with more complex speech environments, noisier environments, and mixed languages and so forth. So this is a very valuable proposition in terms of compute offload. Also, performing compute tasks that can't be done on device. So, volumetric visualization of data that takes big data sets, processes that, and creates a 3D render. That's the kind of thing that you can't currently do on a ODG or HoloLens. They have rendering limits, they have compute limits, and so we can deal with that and perform tasks on the network edge and then bring that data down and process it locally on the device. So the other thing is augmenting control systems. So you can imagine that you have multiple people interacting in a space. You want to be able to facilitate very low latency connectivity, or even remotely, a surgeon controlling medical equipment, or people controlling devices that have to relate to each other based on IoT data streams. So if you're managing wind flow through turbines, you have to control those turbines on a dynamic level. And so this kind of processing of data has to happen very fast, and it has to happen with very low latency to get everything coordinated properly. So with 5G, real quick overview, we're basically starting by deploying it over the existing infrastructure, right? So there's somewhere around 200,000 plus LTE antennas installed in the United States. We use that existing infrastructure. We layer on top of that to deploy 5G technology. But that only works with certain frequencies that are being used. So one of the big things about 5G is moving to support higher frequency ranges. And we do this through a technology called millimeter wave. This allows us to do very, very high bandwidth, high burst data transport, but requires that the antennas are physically closer together. So they have to be positioned within 150, 200 meters on average, line of sight connection between them. But this allows you to move data at incredibly fast speeds. So this is a very important move that's happening, but it will require probably doubling the number of antennas that we've created. So that's the big challenge everybody has right now, is building out the infrastructure to support millimeter wave. You can see here in the image that you can imagine that one of the common ways that these type of millimeter wave antennas would be installed is by positioning them on light poles, because there are already existing infrastructure that we can leverage that have electricity and they have position. And so we can place these in city locations and urban locations with enough density that don't impact the existing infrastructure, and you don't have old ladies freaking out about how it's going to affect the price of their home. Because there's now a little box hidden on top of their light pole that they never even cared about anyway. So this picture sort of illustrates how you have 5G connectivity impacting different areas of your life experience. So here in your car, in your in the infrastructure behind you, you can see the windmills I was referring to. Even the trash can could have IoT data sensors in it and transport data. You're going to see this infrastructure basically create a more and more connected world where everything knows where it is, what's happening with it, and you're able to get that information in real time. So the one thing I really want to emphasize today is that 5G brings a lot more than bandwidth to the table, because most people, when I ask them, what do you think 5G is about? It's like, I can download my movies faster, Things are faster, I get more bandwidth. And that's true, and it's significantly better. But there's a lot of other really big value propositions that people aren't really aware of about 5G. So, the latency is obviously a very important one. The standard spec is to have 1 millisecond of basic radio latency. So that's real fast. On top of that, you start dealing with distance. So, every 200 kilometers that you transport data takes a millisecond. Because we operate at basically around 2/3 of the speed of light when we transport data on the fiber optic backbone. And so you have to factor in distance to things. That's why bringing the compute infrastructure closer to users matters, because then the data doesn't have to go as far. We can reduce that latency. We also have better use of spectrum with 5G. So we have more efficient use of the existing spectrum that's out there, and that benefits, of course, the telco operators, but it also means that we can reduce the congestion, especially in highly dense areas where you have like a lot of people at a stadium. Everybody's at the stadium watching Golden State Warriors, and they're all trying to shoot video and Periscope or whatever up to Facebook Live, and it's taking a massive amount of data upstream, and you need to have the bandwidth to deal with that. So this is a very important aspect of how 5G can benefit everybody. The other important thing is, and to me, this is really kind of one of the most crucial benefits of 5G, is the benefit of reducing or making more accurate the locationing work. So today, GPS is on average about 4.9 meters accurate outdoors, and then it gets really bad as you move around inside of cities, and then it can fluctuate to like 30 to 40 meters away from where you are, and with heuristics on maps, you can end up in another block. So that's problematic for a lot of use cases that we want to build with pervasive AR applications. So getting that down to under a meter is a defined goal of 5G, and also supporting that indoors as well as outdoors. So this means that we no longer have some of these problems. Right now, everybody's building either outdoor mapping or indoor mapping. But what happens when I walk through the door of the building? Do I have to switch apps? So I don't want to see that be the experience. So we want to build a more cohesive and consistent, reliable, predictable experience, and having the ability to get that accurate positioning flow continuously, no matter where you go, no matter how dense the buildings might be. This is an important part of 5G. So bandwidth, of course, is important. So today we have peak 1 gigabit per second data transport. With 5G, it's 20 at line of sight, millimeter wave connectivity. So it's quite a bit different. And reliably, you can expect to get in a consistent mobile versus stationary, when you're moving around in a car or whatever, 100 megabits per second consistently. So that's a very important reliability that you get out of this. So pervasive XR, the talk is titled AR, but it's really about XR, because it's about the immersive, mixed reality, kind of merging things together. There's all these different phrases, so that's really not the important point here. But it's really about creating a continuous flow for the user that's contextualized. And you contextualize a lot by knowing where you are. So that's why this consistent, reliable, high performance, predictable access to where I am is very important. 5G can give you positioning within about 30 nanoseconds. So that's very quick. And that means that even as you move around, you can get updated and be correct very quickly. As the latency goes down, that matters even more. So edge compute combined with 5G can really change the game for us in terms of how accurately we can track ourselves inside and out. What we're really trying to do is take the mobile phone and put it back in your pocket. And eventually, we see that the mobile phone will become the less dominant device, and your glasses and maybe even augmented reality contact lenses will actually be your core device, along with other wearables that you have to measure your hand position. You might have wrists devices. You may have a battery pack in your belt. You may have a necklace, which is actually a battery collar. These devices are going to interoperate together to create the sort of cohesive experience that you have. And so this is all going to be driven by having the ability to offload some of the compute and add layers of compute elastically to the device experience, as well as make it happen in a fast and reliable or consistent way. So one thing about edge compute, which is very nice, is that you can then create a predictable network of latency. And as the user drives around and goes through different places, we can actually detect in advance, predict what the latency is going to be, and it can inform the application and how to operate based on that. So this is my last slide, is sort of a recap of everything I've talked about, which is that basically edge compute is going to get us to this holy grail experience, because we'll have the ability to reduce the form factor, offload a lot of the compute and energy drive on these devices to the network. We're going to build devices, or we're going to see devices being built that have LTE connectivity in them in the next year, and you'll probably see 5G connectivity in about 3 years on these devices. So that's a big part of what's going to happen. By getting the latency down to under the 5 millisecond range, we can start creating a tactile internet where things can really feel like they're happening in real time, even though you're interacting with something that's 100 kilometers away in another building. And that's going to enable a lot of use cases that aren't currently possible. And really, ultimately, the goal here is to enable the pervasive experience of contextualized, personalized information flow and interactions that you do through glasses, and a multimodal experience with speech, hand gestures, wearables, eye tracking. Those will all be able to enable these pervasive experiences to happen in combination with the back-end network and infrastructure support. And so my goal, my vision is in 5 years, we have users of glasses who basically the only time they pull their phone out is actually they're pulling a foldable tablet out, so they can do very dedicated use case specific work on their PowerPoint or a Word document or what have you. I think for the most part, my goal is that when you go around walking around with your glasses, you're able to enjoy a richer, deeper, personal, and contextualized experience wherever you go. And for people who travel and people who are in work or at home or at play, in those modalities of life, I think that we'll able to achieve that over the next 5 years with edge compute and 5G. Thank you very much.